Alright, ladies and gentlemen, so we're going to look at 6.4, which is all about exponential growth and decay. But our real goals for this video, before we start talking about growth and decay, is to first define and solve separable differentials. Alright, so differential equations. So first and foremost, what is a separable differential equation? Well, it's simply going to be a differential equation of the form dy dx equals f of y times g of x. So notice what the difference is. You have a term f of y and a second term g of x with two different independent variables. So when a situation like this happens, we call it separable, all right? Which means that we can separate it out to its respective differentials. And so what our goal is to separate it. So why does this end up happening here? Because separable, we can separate and distinguish our y's and our x's. And so we are going to separate them. So let's say, once again, I have dy dx equals f of y times g of x. I want to get the differentials of y's matched on up together. And I want to get the differentials with x's matched on up with the function that has x involved. And so I need to kind of maneuver to get my x's on one side. And so I'm left with dy equals f of y times g of x dx. But then I need to get the y's matched on up together as well. And so our goal will be to separate in this current form. Dy over f of y equals g of x times dx. And so that is what our goal is really going to be, is to get it into this form right here, to separate our differentials. And that is where the separable comes from. And once we do so, it allows us then to integrate both sides and find an actual equation or a function of y itself. Because remember, you cannot integrate something with a y in terms of a differential of a u, or a x in terms of a differential of a y. Remember, the independent variables and the differentials have to match on up. So let's take a look at an example as to how we can actually use this. So the first example says, solve for y if dy dx equals the quantity of xy squared. And then we have an initial value saying that y equals 1 when x equals 1 as well. So let's take a look here. So now the first thing I want to do is, I can first kind of rewrite this as dy dx equals x squared y squared. Well, why do I want to do that? Because remember, my goal is to separate them on out to each other. And so let's match left sides with y's and the right side with our x's. So this leads us to show that we have dy over y squared equals x squared times dx. By doing this, it allows me to go ahead and to anti-differentiate, or take the integral of the left and the right-hand side, now that the differentials match on up with the variables. So let's integrate and find out what a value or a function of y is going to be. And so if I want to integrate y to the negative second dy equals the integral of x squared times dx, well, I'm going to raise the power and divide by the power. So dividing through, that will end up being a negative y to the negative first power equals x cubed over 3 plus our constant of integration. We want to put that constant on the x side, guys, because we're going to end up trying to find y in the end. But because we do want to find what the actual value of y is going to be, we have to take into account what the initial value was. So it lets us know that y equals 1 when x equals 1 as well. So let's take a look. So it's true that we can go ahead and substitute this on in. So negative 1 to the negative first power here, okay, equals 1 cubed over 3 plus c. Well, here we have negative 1 equals 1 over 3 plus c. And then in the end, we see that c is going to equal a negative 4 over 3. So here is our value for c to substitute back in. And so this will take us to now show y, or negative y to the negative first, will equal x cubed over 3 minus 4 over 3. But we're not done, because we want to solve for y. That was our goal of this problem, is to solve for y. So I'm first going to go ahead and get rid of this negative by multiplying by a negative or dividing by a negative on both sides, just taking the opposite. So y to the negative first. And then I'm going to just rearrange. The negative and the negative become positive, so I'm going to put the positive 4 up first, minus x cubed, and that is the common denominator of 3. Well, now I have y to the negative first, but I need y. So remember, y to the negative first just kind of means that reciprocal. So I will just swap these on out and get y equals 3 over 4 minus x cubed, and that is our function for y. Okay, and so let's kind of think here for a little bit of a concept. Is, sometimes you might be asked about the domain and things of the nature, and so kind of be cautious of that. Think about the possibilities. This is over the interval, basically from 1 to 1. And so you can always double check that this does make sense for an interval from 1 to 1, because on the domain, specifically here, it's something crazy that we're dealing with. It's going to see that, all real numbers are going to work, for this case. But just kind of be on the lookout for things like that as well, too, what the possibilities could be for the domain itself. So, speaking of which, give this one a shot. You've got dy dx equals x over y. This initial value is y equals 2 and x equals 1. You want you to solve for y and find out what the possible domain was going to be if there is going to be issues with this domain here. Alright, so give it a shot. And your answer is down here as well too, guys. This is your final result, so make sure that you can give that one a shot.